Out here? The Philly cheesesteak, something. I've never had that in college. In my life. I've never had that. Everybody talks shit about it, and they always have it. They're always like, Jack Box is terrible, and then everybody goes, I still haven't tried it yet. Curly fries? I'm gonna be asleep.
I haven't forgotten.
No, it's okay.
So, I was asked to do a problem, or maybe more from homework, which we're going to do. First thing, today I'm giving a practical exam for another professor, so my office hours will start at 12:30. I'm really disappointed my grader didn't get the papers back to me like she said she might, but she will get them back to me by 2:30. So if you want to see your homework, you can come get it from me in my office after 2:30. After that, I will put it in the office, so you could go into the math office, talk to Christine, and tell her I want to get my homework from Mr. Schultz's class, and she'll have it. Before we do this problem, I have kind of I want to get this thing out of the way here. I just put up some, I just made up some function here, and I put it on Desmos. And, we see a graph here, and it kind of curves around, goes down. And I wanted to make a point about it for later in the class, not much later. We zoom in. We zoom in here. Notice that this peak here, it was kind of like this, and it got flatter. And if I zoom in more, I get flatter yet. And you kind of see where we're going here. If you zoom in far enough, it starts to look like a flat line. And that's a feature of any, well, almost any continuous function, certainly any polynomial. You zoom in on it, even though it might curve around, if you zoom in on a small spot, it's going to be very, very flat, very much like a straight line. So it's just food for thought will come up. I'm going to turn this off. Okay, so Lillian, I think you had a question. I hope I have the homework page.
Yeah, I have a couple.
Page number?
224.
Oh, I don't have it. But, that doesn't mean we can't do it. You just have to tell me the problem.
Okay.
So this is
F of t.
page 224, what number?
Number 11.
Number 11.
F of t equals, and then in parentheses, ln of t squared, that kind of parentheses. Do you want to see it?
You want to write it on the board?
Yeah.
Okay, good. I can just relax and enjoy what we other work on here. Okay, what am I supposed to do with that? find the derivative?
Yeah.
Okay. So, all of these kind of complicated things, this is a little complicated, you want to break it up into pieces. The first piece you want to break it up into, since this is a multiplication, is the product rule. So the product rule says that the derivative of f times g, not this f obviously, is f g prime plus g prime f. So let's write that down. So f is write this clearly. Log of t squared, that's my f. You have to, I mean, you can write this out explicitly if you need to. Is that Emily?
Yeah.
You have a homework. You can write it out explicitly, but I'm not going to do that. You'll get to where you don't need to. A derivative of sin of t plus derivative of ln of t squared times f of t. Now some of this you could have just saved a step, right? You could just go, oh, I know what the derivative of sin of t is. Hopefully, by now you know it's cosine of t. Well, that's it, right? We just have to deal with this now. So how are we going to deal with ln of t squared? Well, we need to use the chain rule, right? This is like f of x squared, where x is the ln of t, right? And because it's to the second power, we can use the power rule. So this becomes 2 ln of t to the 2 minus 1, or just 1. And then the chain rule kicks in, and I need the derivative of the log of t, 1 over t. Okay, so here I have this not very friendly looking expression, but that's fine the way it is. You could take it another step. You could take out ln of t as a factor, and you have ln of t cosine t plus 2 sine of t over t, but there's nothing else you can do with that. It'll be fine. Yeah. Someone wrote this. Well, I have to think. Well, they know the product rule. I have to give them some credit for that. Why did they leave this? Was it under pressure they forgot? Maybe they didn't know how to handle this. Yeah, that's a subjective thing. But this is definitely all you need. You don't have to multiply constants together or lowest common denominators or anything. Here's a denominator. You don't have to put everything over a common denominator. Now, in doing a real problem where you have to use this, maybe you do need to go further, simplify. Or, if I said, show that this equals some expression, you might have to manipulate it to show that. But that's something like that is unlikely to show up on this exam. So, okay. Any other problems you'd like me to look at? I guess I'm going to add one more announcement, because even though you should all know it, it's come upon me. There's a midterm on Thursday. If for some odd reason something happens, you're in a bicycle accident, you catch COVID, please let me know. Please send me, if you can, you might not be able to, send me an email so we least I'll know what's going on. Ifan, I have a and one last thing, I guess the person who owns this wasn't here, or maybe they were, but it has no name on it. I think there was another sheet on top. This looks like your handwriting. Take it up. Okay, any other homework problems? Yes?
Number 22, please, same page, so.
You guys need to get a fun meet together and take this young lady to lunch, because she's the only one who's brave enough to ask a question. Yes, number?
22.
Number 22 on page.
224.
And would you do me the favor of writing it up again, so that I don't have to flounder around like a fish here? I would say that last problem, it's not trivial, really easy. There will be some really easy problems on the exam. It's kind of medium. Everybody should be able to handle that. Ooh. Now, this is often scary because it's like an exponent, and it's not just x, right? We know that the derivative of e to the x would be just e to the x. But this is again a composition, therefore a chain rule problem. And once you've done a few of these, you should learn to like them, because they're kind of easy in a way. All right? Right? This is e to some function, right? So the derivative of e to some function is just e to that function times the derivative of that function. So really, we already know that this is going to be e to the x squared log of x times the derivative of x squared log of x. So this is the only bit of challenge here, and it shouldn't be that much. It looks like a product, right? X squared times ln of x. So the derivative is going to be x squared ln of x. X squared times the derivative of ln of x plus derivative of x squared ln of x. All right, ln of x is 1 over x, so this is x squared over x. Derivative of x squared, you should just pop out of your head at this point, is 2x ln of x. So we just end up with x plus 2x ln of x. And that's just you'll just have to replace this over here. Right, you could take that factor of x, no importance. And again, this is, medium, it's not hard, some are a little bit on the hard side of medium in difficulty. There might be 1 or 2 hard problems. I'm just, you don't have to take my evaluation. I'm just giving you a scale. There might be a couple hard problems. If anything was, seriously delinquent in terms of an exam problem, something that would throw people.
So what was the full derivative? What was the complete answer? It's E what?
E x squared ln of x times x plus 2x ln of x.
And then we leave it. That's it.
No, it's fine. I don't know what else you would, I mean, like I said, you could make it this.
That's good.
Yeah, that's fine. If you like, it's prettier, but it doesn't really matter. I was going to say if something was really hard and really confusing, it wouldn't be a regular problem. It might be like an extra credit problem, which you can ignore. Okay. So I'm just wanted to double check. So Lisa, Montserrat, Arian, Lorenzo, Ija, these are people missing. Alexis and Ivy and Danny. And, oh, see, that's why I do this. You're hiding under that hat. Sorry, I missed you. I won't try not to do that again. And Jose, who's never come to class, so I don't think he's going to be here for the exam. All right, any other problems? Yes?
Do you have the book up there?
No, I have some pages from some of the homeworks.
You have 251 under.
No, but
I don't have all this stuff.
does anyone have, say again, 251?
Number 8.
Number 8, can anybody take this up on the board? I'm sorry, number
251, number 8. The page.
number 8. Okay.
Yeah, the page is 251.
Can you write that?
I don't, it's a word problem, and I only have some of the words. But
The area of a triangle with side lengths A and B and contained angle theta is 1/2 AB sine theta. K equals 2 centimeters, B equals 3, and theta increases at the rate. Oh, it's a related rate problem. Can I borrow this?
yeah, go ahead.
Yeah. So let me get all this information up. So, now you drew it as a right angle, but it's right triangle, but it didn't say that, did it?
No.
So we've got A, B, theta, and side A is 1/2 AB sine theta. So if little a is 2 and b is 3, and theta increases 0.2 radians per minute, how fast is the area increasing when theta equals 7/3?
No, it should be pi.
Well, 5/3 at 5/3. Okay, thank you. This isn't making sense to me, but that's all right. So we're interested in the area, so probably we want to know what h is. So if we draw a perpendicular here, so h is the height, and b is the base. How convenient with that turns up that way. So, what is h? Well, this is the hypotenuse. So h over a is the sine of theta. We'll know what this means later. So h is a sine of theta. Right? This is a sine of theta. I'm just, gathering the information I know. If you really forgot all the geometry and trigonometry you learned, you're going to have trouble with this part. Okay, so the area has to be 1/2 a. There. 1/2 this times b. So AB sine theta. Yeah, that's the area. Oh, that's what they mean. Oh, I thought they meant, this angle. I don't know what I was thinking. Forget that. Oh. So they're just telling you, the area here. And theta is increasing at 2 rads per minute. And at some point it's pi over 3. Okay, so now we want to make up something, some version of the chain rule that is going to apply to this. So clearly one of the features is going to be d theta dt, which we know. And we've also got an a dt, it's the area. So we could write the area dt equals what? Theta dt times what? The a d theta. Oh. I didn't really think geometrically about that. I just fiddled around with the variables. So that looks like the right version of the chain rule we need for this example. And what do we know in here? Well, this is what we want to know, right? Is that what it asks for? How fast the area is changing?
Yeah, how fast is the area increasing when theta equals pi over 3?
Yeah, okay. Pi over 3. First we're going to find it in general, but then we'll plug in pi over 3. The theta dt, they tell us, that's 0.2. So this becomes our short, d8, the area d theta. But we have this as a function. Area with respect to theta is 1/2 ab sine theta. So what's the a of dt? No, the a d theta. That's what we're missing. Anyone want to hazard a guess? I wonder if, I know this is it's a real thing. You see a weird Greek letter and, your brain gets a little scrambled. Oh, I haven't seen that before. Maybe not in this context. If it helps, you could write it f of x equals 1/2 ab sine x. Does that help? Maybe. You want to get to where it doesn't, where you just look at this and you understand it's the same thing as this. All right, well, we get two constants here. As far as we know, a and b don't change. So they just stay out in front. And now we just need the derivative of the sine, which I hope, I hope it's kind of burrowing in, so you know that it's the cosine theta. All right, so what do we got here? Let's write this as some kind of problem. X equals 1/2 AB cosine theta times, I'll just write it as 2/10. All right, and we want to evaluate it at pi over 3. All right, so just writing this down on an exam for a problem like this would get you a lot of points. I'd be disappointed if you couldn't tell me what cosine of pi over 3 is, but that could happen. But you might want to draw a triangle. You might want to remember that pi over 3 is how many degrees? It's my conversion. 60 degrees. So this is a 60, 30, 60, 90 triangle. And the cosine, that's the adjacent over the hypotenuse. Well, this is 1, this is a half, this is square root of 3 over 2, so the cosine is going to be 1/2 over 1. So this is just going to be 1/2. All right, so what do we end up here? 1/2 AB times 1/2 times 2/10. Get rid of 1, 2 there. So AB over 10. Oh, did they tell us what A and B were? 2 and 3. 6. 6 over 10 or 3/2. No, 3/5. So that would be how you would solve that. You have to break it up into pieces. If you feel more comfortable plugging in the A and B early, so you just have a number here, it's fine. All right. Those related rate problems are, do the homework, get some practice. Ask me for more if you need them. They're one of the, doing the problem isn't hard, it's figuring out how to do it. It's usually the hard part, especially the geometry or trigonometry involved. All right, any other? I filled up like a whole blackboard here. I should tell you something about doing these. I mean, use paper, you can recycle it, we won't be chopping down too many forests. Or, I don't know, use like a tablet, that you can erase. Etch a sketch, whatever those things were we used to have. Okay. We have 2 subjects to cover today. I hope we can get through both of them because one of them involves bubbles. Let's see if we can get to that. First subject is linear approximations. And the idea is, kind of like what I was showing with that graph, is that if you kind of zoom in on some function, that if you're a small distance, small h, away from your point, that a line is a good approximation for your function. It's not good out here, it's not good over here. But very close in, it's a good approximation. So this is a technique, linear approximation, which comes up in the sciences a lot, economics, other fields. And you're usually using it in a real-world situation where, you want a quick, easy approximation. It's all right if it's not perfectly accurate. The world isn't perfectly accurate. Measurements aren't perfectly accurate. So we start with this very important equation we've seen, the definition of a derivative. Which you really should be familiar with. And we relax the condition here a little. We're not going to find the limit as h approaches 0. We're just going to exchange that for h is small. So we can take off the limit, put it in an approximate sign because that's what it is. And since h is not 0 anymore, it's just small, we can multiply through by h. And we're going to take one more step. We're going to add f of x to both sides. We're moving it from here. So, and I'm going to switch the order here. So we get f of x plus h is equal to f of x plus h times f prime of x. So what is this doing? Well, f of x plus h is what we want to approximate. That's some point out here on the tangent. And, well, actually, I'm sorry, it's on the function, but we're going to approximate it with the tangent. And we approximate it by the value of f of x, of f at x, plus little h times the derivative at x. Now, we could go through a long derivation showing that x plus h, this is f of x. I could show you that this is exactly what we do when we find the tangent, right, or a point on the tangent. But I'm going to leave that. If you're interested in that derivation, you can look in Stewart. I think this is it's pretty self-evident. We take a point on the curve, we take the tangent, we take h times the slope, and we get this point on the tangent, which is close to the point we're trying to approximate. All right, at this point, this feels a little unnecessary. We have some function. We probably can find the derivative. We probably can, or we probably can find f of x plus h if we have a definition of x. Maybe we don't. Maybe we just have data points, and we're trying to estimate it. And we have some model for what the derivative should be. The book comes up with some problems for us to do that try to demonstrate that this is really useful. And I don't want to downplay, they look really useful. We all have calculators, so I don't know how useful it is. But the idea is the thing. It also helps to imagine that the book is written probably That probably is written before everybody had handheld calculators, so this stuff seems more useful. Let's try something really simple and obvious. Say our function is square root of x, and we want to find f of 104. Well, there are ways to find the square root of 104 that are mechanical, but we're just going to, we just want an approximation. So we're going to make this f of 100 plus 4 for reasons that will become obvious. So our linear approximation formula tells us that f of 100 plus 4 is approximately equal to f of 100 plus derivative of f at 100 times 4. Now, is 4 really small enough for a good approximation? We'll see. In different contexts, it might not be. It might be a smaller number. But okay, so what do we got here? F of 100, that's square root of 100. It's kind of manipulatively easy. F prime, derivative of square root of x, I guess I should, prime of x is equal to 1 over 2 square root of x. That's just applying the power rule, x to the 1/2, so 1/2 x to the negative 1/2. That's the derivative, so this is 1 over 2 times the square root of 100. Again, kind of manipulatively easy, times 4. And now you kind of realize that with a little, a little effort, you can do this in your head. So it's 10 plus 4 over 2 times 10. 10 plus 4 over 20, right, or 10.5. Okay, that's our approximation. It's worth comparing that with what it actually is. Well, we can't really write what it actually is. You can plug this into your computer and get more digits, but it's approximately, oh, I've regressed, I can't do fractions. There we go, 1/5 is 0.2. It only differs by 0.002. And if I divide 0.002 by 110.2 is the answer. The error is approximately what? 0.02%. Not 2%, 0.02%. What that small value tells me is that if you look at the graph of the square root of x at 100, and you look at the tangent, that, within, 4 of the tangent, the difference between the tangent and the function is very small. You can approximate it using a linear approximation. That's the main idea. Is there any questions about that?
You're just finding like what the error would be?
That's what I did here. How far off is my approximation from a much better approximation you can get with your calculator. I mean, I could do more digits, but that's not gonna, I only want the error approximately is what I'm saying. So I don't need a, when you're dealing with error, like you have a 45% error, it doesn't matter if it's 45.1 or 44.9, it's a big error. On the other hand, if you're dealing with a small error, it doesn't really matter either. If it's only 0.02%, it doesn't matter if it's 0.023 or 0.024. Okay, similar but more complicated problem. Just want to see that we're on track here. Okay, a sphere has radius 3 and is incorrectly measured. We incorrectly measure r as 3.1. So the question is, what is the error in the volume? And I guess we call this the relative percent error. We want to find the relative percent error here. Okay, well, we're going to start the obvious place. The function here is the volume. Volume with respect to r is 4/3 pi r cubed. It's the volume of the sphere. And since we're going to need it for our linear approximation, dv dr equals, well, here's the variable, right? This is a constant. So the derivative of r cubed with respect to r is just the power rule. So it's 3 times 4/3 pi r squared, and the 3's cancel. So that's our derivative. And our linear approximation formula says that v of r, might as well put this in, 3 plus, what was it, 0.1? So approximately v of 3 plus h, which is 0.1, times derivative f prime 3. Okay, so v of 3 is 4/3 pi 3 cubed plus 0.1 times 4 pi 3 squared. What we got here, we can get rid of 1, 3. So it's 9/36 pi plus 9 plus 36, 3.6 pi. I guess since we're interested in the error, that's just this part, right? Yeah, I guess we don't need this. We're just interested in what the error is. And the error is 0.36 pi, 3.6 pi, over, the relative error, or, we're going to get the percent error is going to be 36 pi, right? That's 4/3 pi r cubed at 3. So this is approximately 0.1, or oh, well. I feel like I left something out here, but I don't. This is just this is 10%. That doesn't sound right. No, that doesn't sound right at all. So the error in volume. I think everything I told you was right. I just have the numbers kind of mixed up here. Yeah, well, my notes say it's 0.1%, and I say it's 10%, so I'm going to go with what I'm saying right now. Did I mess up the calculation here anywhere? I don't think so. I don't know. I may have to come back and correct this at another time. I'll have to take a look. Sorry. We're close. All the ideas are okay here. I'm just kind of mixed up with the numbers. Doesn't look like 1% to me. It looks like 10%. All right. Let's see if it has some input. Let's try one more of these. If you all would take a little paper, and I'm going to use the same function here, square root of x, and if you could estimate the square root of 125, and I'm going to give you the obvious decomposition. Find the square root of 121 plus 4, approximately. Will you work on that for a minute? Give that a try. Remember, you're on a desert island and you don't have a calculator with you, right? Just practicing for later. unfortunately. There you go. All right, someone want to give me, well, someone want to tell me what the first term here is going to be? I often find that unfamiliarity with some basic numbers is often a stumbling block. Does everyone know what the square root of 121 is? 11, okay. Okay, so h here is what? 4. And I guess I could write derivative of square root of x. So this is going to be what? Which is, okay, so we've got 15 plus 1 over 22, which is 15.04545 repeating. And what does our calculator tell us the square root of 125 is?
11.18.
Yeah, what did I do
Can
wrong
you just
here?
take the 11 and the 4 though and approximate 11.2? I don't know.
Yeah, thank you. That ought to feel a little better. Okay, so this was 11 point. And what did we decide it was? The square root of 125 is 11.18. Oh, okay, so down to the third decimal. So if I estimate this is about 182, okay, it's 02 over 11.18 times 100, what's my error? Divided by 1.18 times 100, I get 0.017% error. Yeah. All right, let's take a break for a few minutes. We'll find out what this bubble stuff was about. Pretty exciting.
Yeah, that looks cool. That's like the logo. It looks like a book kind of, like connects up with the other side. Yeah. That's nice. Really nice. Yeah, mine just a square with the H inside. Yeah, it's good for them to. Like it'll be a button.
I'm fairly certain it's probably.
Yeah, it's just like.
It's a 10. No, it's just my terrible handwriting.
So like when you write your name in like one place, it's not gonna look as good as right now, but you know what I mean, yeah. So we're kind of like, how do you spell it exactly?
That makes sense, like, what I did.
Like that?
Yeah, so you can try.
That's many different,
Square with a cross.
that's many, how many problems are on
And then
the
an I and then the A is there again.
20?
What?
Questions on this?
Like flowers? That's nothing.
Much time as you need.
There's like a little hard crosses. Yeah.
It will be mostly like homework problems.
They're not all.
Oh, you guys had it. We could probably just, we could put it.
They're not specifically homework.
I didn't bring it with me.
That probably is homework problem.
Like, you should just give them.
Oh, did you take it already?
It's not
Yeah,
a,
see, it's the same ones.
it's not an attempt to see who could be on the math
Unless I lost it. You said I don't know this, but
I definitely don't have.
unlikely. You also can bring in a cheat sheet.
Back, front, back?
Yeah. Yeah, I guess I can mention that again. Mentioned it before.
Is it one credit or double credit?
One credit or double credit?
No, sided, the note sheet.
It's two-sided.
It's two-sided.
Yeah, you can use both sides. So, I'm gonna get going here. Just had some questions about the exam. First rule, don't panic, right? We'll all be okay, it's just an exam. Learn the material, come in confident you're gonna do okay. You'll have the entire period to do it, and if somebody feels like they need more time, we'll work that out. You can use a calculator like this. The only thing you can't use is if you have one of those TI, whatever, super calculators that does the differentiation that I want to see you do. So this is an 84, that's fine. I don't remember where it cut off. I think an 86 goes over the top. And you have a sheet of paper if you want. You can put formulas, Trigonometric identities, whatever, 2 sides. I find that the main function of those sheets of paper is to give people, to make them a little more relaxed about it. You know, they're not going to just forget some crucial thing. But 9 times out of 10, they really don't need it. You know, if you need it, you might need to look up 1 or 2 formulas. But that's typically what happens. But do, you know, write it up. Write up whatever you want on it. Anything else I want to say? I don't know. That's all I have to say about the exam, unless someone has questions. But again, you know, get a good night's sleep. Don't stay up all night studying the night before. It might help, but it might make things worse. Just, you know, again, just go over the material, feel confident you know what we went over in class, and come in and you'll do fine. All right. I want to talk about, this is like one of my favorite topics in this class, because sometimes math is pretty. You know, you have to use your mind sometimes to see that. It's not always pretty pictures, but so we're going to talk about something called a hyperbolic function today. And we're going to contrast it with what we call circular functions, or better known as trigonometric functions. Circular because you can define them in terms of a unit circle, where the coordinates of a point on this circle relative to the angle it makes, you know, from starting at the x-axis, is the cosine and the sine. I assume you're all familiar with that. In a similar manner, we can start with a unit hyperbola, not unit in the sense of it has a radius, it doesn't have a radius, but its equation is x squared plus y squared equals 1. And it turns out that you can define, you pick some point on here, you can define the area between the hyperbola and this line segment. You can define that as the hyperbolic angle. We'll call it theta. And then points on this hyperbola can be defined similarly as hyperbolic cosine of theta and hyperbolic sine of theta. Now, this is actually a very awkward way of defining it. However, there's a much more straightforward way to define them. In particular, the hyperbolic sine of x is equal to e to the x minus e to the minus x over 2. The hyperbolic cosine of x is e to the x plus e to the minus x over 2. And there's, hyperbolic tangent, which can be defined as the hyperbolic sine, hyperbolic cosine, and the other equivalent functions, secant, hyperbolic secant, hyperbolic cosecant, hyperbolic cotangent are defined the way you would expect in terms of the hyperbolic sine cosine. So let's take a look at least roughly what these functions look like. One wants to be clear, these are not hyperbolas, they're hyperbolic functions. They're given that name because of this, you can define them in terms of this unit hyperbola. Hyperbolic sine kind of looks a little like x squared, but not. Eventually, the e to the minus x term will become insignificant, and this will, I guess I'll use a different color, will become coincident with the function e to the x, eventually, or e to the x over 2, I should say, as this gets very large. The hyperbolic cosine again, it looks a little bit like a hyperbola, but in fact, as it gets further out, it's going to approach e to the x over 2, or negative e to the x over 2 as you go off in this direction. And since we've taken a look at these, we should take a look at the hyperbolic tangent, which kind of looks like this. Since it's going to be e to the x minus e to the minus x over e to the x plus e to the x, you can see for large x, this is going to approach 1. And for very small x, it's going to approach minus 1. So as a asymptote of 1 and negative 1. Now, just on their own, these functions are kind of interesting. Just mathematically out of context of any kind of reality. There are a number of, we'll call them symmetries with the circular functions, which we'll take a look at. So we have the well-known Pythagorean identity for circular functions, sine and cosine. I guess I'll draw a line here. For the hyperbolic functions, we have something similar. In here. We have the, this is also Pythagorean, but 1 plus tangent squared equals secant squared. Well, in the case of the hyperbolics, we have exactly the same. Not the same, it's with different functions, but it looks the same. Oh, I'm sorry. There's a minus sign here. 1 minus tangent squared equals secant squared. Hyperbolic secant squared. If you look at the sum formulas, sine of x plus y, you get sine x cosine y cosine x sine y. For the hyperbolics, sine h of x plus y is equal to sine h of x cosine h of y plus cosine h of x sine h of y. It's very similar. For cosine of x plus y, well, we have a few different versions. Usually we start with cosine squared of x minus sine squared of x. And then you can rewrite this 1 minus 2 sine squared of x, or cosine squared of x minus 2 cosine squared of x minus 1. For the hyperbolic, sum of cosine hyperbolic of x plus y, you get hyperbolic cosine x times hyperbolic cosine of y plus sine hyperbolic of x times sine hyperbolic of y. I don't want you to feel like you need to memorize these. If you don't want to jot them down, that's fine. It's just, we just have this remarkable symmetry in these. I mean, if you look back at the function x squared plus y squared equals 1 versus x squared minus y squared plus 1, you see it's not a complete coincidence. We also have similarity in the odd and evenness of these functions. Sine of x, well, sine of negative x is negative sine of x. That means this is an odd function. And cosine of negative x just equals cosine of x. Making this an even function. And by the rules of odd and even functions, the tangent has to be an odd function since it's difference or product of an odd and an even function. For the hyperbolics, it's exactly the same. Get that h in there. And you can kind of see this right away. This is the hyperbolic cosine, you can see, is symmetric over the y-axis, so it's going to be even. The hyperbolic sine is symmetric over the origin, so it's going to be odd. And the same with the hyperbolic tangent. Now, here's where we get to the real fun part when we get to calculus. Of course, you know that if you start finding derivatives of the sine function, you get the cosine function. You find the derivative again, you get the negative sine function. And if you find the derivative again, you get the cosine function, at which point you can start over. It's a cycle of 4. The derivative of the hyperbolic sine is the hyperbolic cosine. The derivative of the hyperbolic cosine is the hyperbolic sine. So there's just a cycle of two here. It's really easy. Derivative of the sine, hyperbolic sine is the cosine, hyperbolic cosine, derivative of the hyperbolic cosine is the hyperbolic sine. Now, absolutely everything I've just put up on the board is all within your capability to prove. Maybe you start with these definitions here. And I'd like to show you at least one example. Not only can you prove it, but you can do it pretty easily. So, if the hyperbolic sine is e to the x minus e to the minus x over 2, and I want to find its derivative, well, what's that? Derivative of e to the x is e to the x minus derivative of e to the minus x. Well, I have to invoke the chain rule. So it becomes e to the minus x times the derivative of minus x, which is minus 1. So this just becomes a plus. And of course, this is the hyperbolic cosine of x. You ought to be able to do that. Likewise, with a little work, you probably can show the tangent identity, tangent secant identity. I'd say all of these are easily done using these formulations. So this is kind of pretty, you know? It's like, on one hand, we have these apparently useful sines and cosines. It's really useful in all sorts of things we know. You can use them in carpentry, you can use them in triangulation, or if you're a, what do you call that, surveyor. And of course, they come up in science all the time. Now, one important difference is the trigonometric functions are all periodic. The hyperbolic functions are not. So that's a major difference. There's one other similarity I want to show you. When I first ran into this, it was kind of mind-blowing. You might think it's really kind of nice, coincidental that you can write it this way. So I'll rewrite it. Turns out you can write our friends the sine and cosine in a similar manner, but you have to rely on your understanding of imaginary complex numbers and how they relate to trigonometry. So you can write sine of theta as e to the I theta minus e to the minus I theta over 2. And you can write the cosine of theta, e to the I theta plus e to the minus I theta over 2. And here now the symmetry between these two is just perfect. But I'm not done yet. There's so much pretty math here. It's something I always want to do in pre-calc, but I can't because the students don't know any calculus. You don't know something here yet, but you can get away with it. Many of you are physics or science majors, certain math majors. You'll definitely take Calc 2, and you'll run into something called a Taylor series. You don't have to know this. It's just so much fun. Taylor series. And the idea is you take a function like e to the x, and you express it as an infinite sum. Well, okay. We need these coefficients here. And how can we figure out those coefficients? Well, we can start by plugging in 0. All these are going to drop out. And e to the 0 is, of course, 1. So we have a0 equal 1. We can then find the derivative of both sides. So we get e to the x, derivative is e to the x. The a drops out, it's 0. We have a1 x. Oh, no, we don't. We have just a1 plus 2x plus 3x squared, so forth. And we repeat. E to the 0 equals a1, so a1 equals 1. All right? Guess we want to try it again. Again, we find the derivative. E to the x equals 2 plus 3x plus 4x squared. Oh, now when we plug in 0, all these drop out, and we get, I left out something, didn't I? 2a, 2, 3a, 3, 3a, 3a, 4, a2. So a2 is 1/2. Now, if I repeat this, what I'm going to see is this is a3 equals 1/6, or as we like to write it, 3 factorial. This is 2 factorial, this is 1 factorial. Oh, here's an opportunity to see why we call 0 factorial 1. And my a to n is equal to 1 over n factorial. So we get that e to the x is the sum of, what is the sum of? 1 over n factorial, where n is 0 to infinity. Well, what does that have to do with hyperbolic functions? You can do the same thing. And you discover that the hyperbolic sine is 1 over 1 factorial x plus 3 over 3 factorial x cubed plus 5 over 5 factorial to the 5th. It's the same thing as e to the x, just the odd terms. is nice, because it's an odd function. Similarly with cosine of x, you get 1 over 1 factorial. Is that right? No. Yeah. Plus 2 over 2 factorial x squared. This is x to the 0, which is just 1. 4 over 4 factorial, x to the 4th, and so forth. So it's just all the even terms that you find in the expansion of e to the x. Well, this would be even more pretty if there was some kind of similarity to the Taylor expansions of the sine and cosine. What am I doing here? These are ones. Sorry about that. It looks exactly the same as the hyperbolic with one difference. Every other sign is a minus. And the same for the cosine of x. So forth. So there's just this beautiful symmetry between these functions. So as I said, just by itself, there's some pretty math here. If that was the case, they wouldn't be on the curriculum. Some of you, probably a small number, will actually run into these functions in some real-world situation. I don't know how many engineers we have here, but it's my beautiful rendition of the Golden Gate Bridge. Now, of course, you have cables, and the cables have to hold up the roadbed. And we need the optimal, well, we need a shape here that's optimal. This is called the catenary, but in fact it's hyperbolic cosine. That's one example. Turns out that if you're building a dome, you might think the ideal shape for this dome would be a circle. But especially if you're living in, I don't know, the 14th century, you're building a church, and you want it to be strong, right? This is not optimal. It's actually, again, it's a catenary or hyperbolic cosine. And I want those of you who can turn around and look out the window, because we have a dome here. Here, you want to lift up that, yeah, lift that up a little, thanks. So we're blessed here with a demonstration. Now, obviously, just looking at it, you can't tell precisely what it is, but if you're an architect, you're going to learn that that's the shape where the physics is such it holds itself up really well. Better than other shapes. So, all right. The fun part. the final demonstration has to do with this idea of least area. If I were to create two rings and a surface around them, I want to minimize that area. Well, it would take a lot of math to prove this, but it turns out that if you take a hyperbolic cosine and spin it around, which is called a catenoid, well, I'm not going to draw it very well. That's what you get. Well, it turns out that one of the properties of bubbles between frames is they like to take up the least amount of area. That's because the bubbles have surface tension, and again, they're trying to minimize that. So that's why I have all this equipment here. These paper towels to clean up the mess afterwards. I will give you what's the word I'm looking for? Reasons to consider why I may fail. I've done this once before, and it worked. But it doesn't work for long. So if anyone wants to come and sit in the front or move up, to make sure you see it, if it does happen, you're welcome. And if you're afraid of bubbles, well, can't help that. Let's see if I can do this. Whoa! Now, I need an assistant. Quickly. Can you pop the bubble in the middle? Just put your finger in there. And no, not there. In there. Yeah. Oh, okay. Stay here because you might have to try it again. You might have waited too long. No, come on. All right, go ahead. There it is. It's a catenary. Keep pulling it apart until, whoa, there it goes. Shall I try again? It's kind of messy. Okay, go ahead. You get a good look? That's not gonna bite. All right, I'll just stand here until it explodes. So math in action. All right, thank you. That's kind of it. There'll be a few insignificant homework questions on this. But before you go, I will attempt another bubble trick. And I'm going to describe it to you, and then I'm going to say, I don't know how this works. I may not be able to do it, but I've seen it enough. So I'm going to blow a bubble, and then I'm going to put a bubble inside a bubble. That's not hard. Anybody can learn to do it. But if I'm lucky, I will blow a bubble straight through. It will come out the other side, and if you look really carefully, it's not actually one bubble when it comes out. It's two bubbles, one inside the other, very close. Now, I did it once earlier today. It takes a bunch of tries. Get 2 more minutes. Almost. That's just part 1. Practice. I'm not doing well today with this, but that's because there's an audience. I still got another minute. Ah. That's not the good one. I don't know if I'll get the good one. There it is. Do you see that?
Yes,
How did that happen? I have no idea. I expect all the bubble physicists in this class to do this as a project. Explain to me why there are 2 bubbles when it comes out. Now that I've practiced it, try it again. All right. Thank you. Oh, my office hours start around 2:30. If you want to come to office hours today. Yes. I'll answer your question. One more thing. If you're looking for previous homeworks, you can either come at 2:30 or you can ask in the math office after 2:30 for Christine. She will have them. Your question? No. Not on Monday. Not on Tuesday. Thursday, just let me know if you want to come. So I'll be, and, Zoom other times. Yeah, that's good. Same time. It's room 119E Orange. Room 222 is the math office. I'm the next door over inside.
Is it Zappa? In Loma?
In Harnett.
Where's Harnett?
So if you go down the hill
Uh-huh.
and then you jog a little to the left, is the front door of Harney. I think that's Harney. If you know where Losciavo?
It's the
Well,
building
it's attached to it, and it's on the first floor. Okay.
Thank you.
No, you can write love letters to your dearest, and I will not. You don't have to turn them in.
Inspiration for the exam.
Hey, whatever.
Okay, thank you.
Question.
Do you have a moment to just go over a question?
Yes, I do, and if I can't answer your question while I'm cleaning up, I'll stop cleaning up. And if I can answer your question while I'm cleaning
Oh,
up,
it's a math problem. I need help with.
could you then, can I ask you, erase
Yeah.
some board and write it up there, and I will take care of it. Yes, Carl?
I have the same kind of question. Just
Well, you could, when she's done erasing, you could get the eraser, and you could erase another part of the board and write it up, and we'll go over it.
understood.
And you said there's no due date, not specific.
Well, the year 2016, 2036, no.
No, yeah. Can I just,
Try not to abuse it.
okay, but can I turn all my homework in on like Thursday?
Yeah,
Okay.
yeah. That would be fine. Whatever you haven't turned in up till then. Yeah, that would be fine. You have one more?
Yeah, I split it up into three because there is some.
That's okay, that's fine.
I also wanted to share with you the most interesting right now, because you started talking about the hyperbolic functions.
Mm-hmm.
I actually got there's a calculus 2 video recommended in my YouTube.
Okay.
And so I was actually wondering like all that stuff with like the cosine reach.
Mm-hmm.
But it was with like integral and stuff like that.
Mm-hmm.
So I just thought that was interesting. I wanted to share with you.
Thank you. Yeah. Yeah, no, you know, it's funny because
Sorry.
they're not even all that sure they want professors to do hyperbolics. It's sort of like optional. And I just think, you know, well, yeah, I can see why, but it's one of the most, you know, to me, it's one of the most, it's just where math, you know, it's pretty in and of itself. You don't have to apply it to something else. Okay, I think I clean this up now for the homework. Okay. Use logarithmic, oh, yeah. So y equals, is that squared?
Mhm.
Plus 2x to the fourth plus
4.
4 to the fourth. So you could just multiply this out and use the power rule. But the way you do it using logarithmic differentiation is you say, well, this is the limit of y, which is the limit of all this stuff. Which is because the log of a times b is the log of a plus the log of b. So now we find the derivative of both sides. Now this, we have to use this idea of implicit differentiation.
And
This
then
is-
y prime over.
Times y prime. This becomes a lot easier. This is 1 over x squared plus 2 times 2x. Derivative of log of x is 1 over x, so the derivative of this is 1 over x squared plus 2 times its derivative. Same thing here. 1 over x to the fourth plus 4. Oh, wait a minute. Wait a minute, wait, hold on. Oh, I forgot something. I have to do something. This is this, right? So this is 4, and then 4x cubed. Now the only problem here is this y over here. So we put y over here. But what's y? That's y is x squared plus 2 times x to the fourth plus 4. So that's the solution. Now, if you want to simplify it, you can, but this is a perfectly good answer. This is the derivative. Some of these logarithmic differentiation problems you can do a different way. I mean, this would be painful, wouldn't it? Right? You could do it. But here, it's pretty straightforward. Some problems we don't have another way to do. Like, I think I showed you y equals x to the x. We don't have a way to do that without logarithmic differentiation. Okay.
This, because you have y in here, you move it over to
Oh,
this
oh,
side,
I see.
y is this, so.
Okay, so. Oh, yeah, I'm not sure what this problem is. Is this the problem?
Yeah, that's the, you gotta find, I guess, find that.
So this is a composition, log of the secant. So it's a chain rule. So you can think of it as y equals log of u equals secant of x. So dy dx equals dy du du dx, that's one way to break it up. And what is that? dy du. Well, dy du is 1 over u. dy dx, secant is the secant of x times the tangent of x. But we don't want to leave this way.
So it's-
U is the secant. So 1 over secant times tangent. So it looks like it's just like the tangent.
Yeah, because these are also.
Yeah.
Tangent.
Yeah. Now, if you get efficient at this, you just look and say log of something, that's 1 over the thing, times its derivative. Secant times tangent.
Oh, I see what you did. Okay. If you don't do this or if you do this way.
Well, this is writing it all out,
Yeah,
being
yeah.
explicit, but,
Uh-huh.
you know, you can get good at this, you know.
Yeah,
It's the
okay.
same if I said e to the secant of x, you go, well, that's just e to the secant of x times secant times tangent, right? It's kind of a mental, you know, like you do addition in your head all the time and you don't really think about it. But with a little practice, finding derivatives ends up this way.
Yeah, I do like this way.
I'm like a monkey copying down Shakespeare.
Okay. Monkeys don't copy Shakespeare. They randomly type until they get Shakespeare.
Oh yeah, that's me right there. So you can take